So we'll pick up kind of where we left off. We'll do a little bit more work in Excel and then kind of jump into the next topic today. So especially for next week, make sure you get that third Learn Smart done by the end of the day on Friday this week so that we're ready to really dive into that next chapter. We'll be talking about it on Friday, but some of the stuff that I want to make sure you have a look at that we're going to talk about next week is in that Learn Smart. So make sure you get on, get those easy points. There'll be an online quiz today that's due before class on Friday. It should be pretty easy. Once we go through today's material, I'll probably even mention kind of what the questions will probably look like. You'll kind of see we're meeting in a different class right now. Actually, probably I might have like a 30-second delay here in a second and go down and make sure that no one's in the old class. But group 1 and group 2, I kind of assigned group 1 to Wednesday, group 2 to Friday, and then we'll just kind of alternate classes, right? So you can kind of show up every other class, okay? Based off of the response that I got for those who want to attend in person. You can already see we're missing a few people even today, so that list might dwindle. Maybe in a month or so, we'll see. We'll kind of reevaluate and maybe get people who want to show up in person, almost be able to show up every single day. But for now, kind of every other day based off those groups, okay? So with that being said, I'm going to run down there real quick and see what's down there. All right, no wins there. I switched my other section. I had someone waiting down there, so I got a little paranoid. All right, so let's kind of jump into it here. So left last class off talking about kind of how we create these histograms, right? These frequency distributions, putting them into a graph, okay? So I believe we kind of worked through how we do that. You can, instead of doing a column graph, you could make it a line graph. I'll show you how to do that here in just a second. But we're going to talk about, kind of start the class off talking about cumulative frequencies, right? So we'll revisit this Excel file, and I'll do a little bit of work up here kind of on the board, right? So we calculated relative frequencies. We had percent frequencies. I think at the end of last class, I changed the number the other class showing them something. So let's go back to that 525,000. So we left that off last class. I think we ended with these relative frequencies. We said one way to check, because they represent the proportion of observations that fit in this bin, and every observation's been counted once, the relative frequencies should add up to 1, right? Because it should be adding up all the proportion in every bin. If every observation has been counted at least once, we should have the total number of observations divided by the total number of observations. So those relative frequencies, if we use that sum function in Excel, they should add up to 1, okay? Similarly, the percent frequencies should add up to 100, okay? So with that in mind, let's think about cumulative frequencies, okay? So I might try to do this in Excel because I think it might give a nice visual. So let's select these labels, hold Control or Command on a Mac. Let's select my frequencies and just create one of these column charts, okay? So if I have this nice visual here and kind of can see what these values are, the cumulative frequency, right? For no matter what bin we're looking at, the cumulative frequency, it's very similar to your GPA, okay? So your current semester GPA looks at your grades this semester, right? Your cumulative GPA looks at your grades from this last semester going all the way back to your very first class, right? All the way, everything that's below it, okay? It's the same idea for frequencies. A cumulative frequency for the first bin is really easy, because if the definition of cumulative frequency is take the frequency from this bin and every bin below it, well, for the very first bin, take its frequency. What's the frequency of the bins below it? Well, there aren't any, right? So all I have to do is that cumulative frequency is just whatever the frequency was for that bin. Now for the second bin, whoops, sorry, hit enter. For that second bin, the cumulative frequency will be the frequency of the bin that we're looking at oh, I forgot my equal sign. The bin that we're looking at plus the frequency of every bin below it. Well, there's only one bin below it, so we'll add that frequency in to get the cumulative. Then we go to the third bin. We'll take its frequency and then add to it the frequency of every bin below it. And we will kind of continue this process, whoops, until we get to the very last bin, where we will be taking, right, its frequency plus, here I'm going to cheat, not cheat, do a little shortcut, plus all the other frequencies below it, right? Okay. If I do that, I should get a cumulative frequency for that last bin that's equal to the total number of observations, right? Because really what I'm saying with the cumulative frequency is how many observations are in this range or any other range of values below it. Well, that covers every possible value I could ever see the variable be, so every observation is going to be counted by the time I get to that last bin, right? So when I get to the cumulative frequency for my last bin, it should always be equal to the total number of observations, which we had over here, so that's good, right? But, you know, I'm doing these by hand for every single cell. There's another process or an easier way to do it, okay? So if you think about here, right, I've got my frequency for this lowest bin. That's just going to be my cumulative frequency because there's no other bins below it. So that one's always easy. But another way that I could do this instead of having to type this in for every single cell, what I'm doing is saying, well, look, take the frequency of the current bin and add to it the frequency from the bin below it. But notice, if I were to add in the frequency of the bin below it, it'd be the same thing as taking the cumulative frequency from the previous bin, right? Those are the exact same. Okay? Oops, sorry. I have to add that in, don't I? And add in that cumulative frequency from the bin below it, which I have here in cell 07, right above it. Now notice here, if I want to do the cumulative frequency, I would take the frequency of this bin plus the frequency of the bins below it, but the frequency of the bins below it, if I add these two up, well, that would have just been what the cumulative frequency was from the previous bin. So I can just say, take this bin's frequency and add to it the cumulative frequency that's right kind of behind this blank space from the bin below it. So here, 08, right? Gets me the same numbers. Now I can't copy this one down because I continually had to like always add in one more cell. But with here, when I copy this down, when I get to down, it takes the frequency of this bin, adds to it the cumulative frequency from the bin below it, right? So that's kind of an easier way to do this in Excel, all right? And really what it's coming from is the cumulative frequency, right, for the previous bin would have represented the sum of all the frequencies that were below that current bin you're looking at. So another way we can think about this, put some different numbers to it just so we get a different look. So I don't know, we'll come up with some bin widths here. So let's say this is 5, this is 3, and this has a frequency of 1. Okay. So these are my original frequencies. If I wanted my cumulative frequencies, and I'll kind of move out of here in a second, although even for those of you in class, you can also, it should be up on the screen right now. So if we want to come up with the cumulative frequencies, for this very first bin, it's easy, right? It's the frequency of this bin plus every bin below it. There are no bins below it. So we start out with a cumulative frequency of 5. I want a cumulative frequency for the next bin. Take its frequency of 3, add to it the frequencies of the bin below it. So you can almost think about here. So it would be what, 3 plus 5? Really, this cumulative frequency is made up of the current bin's frequency plus the frequency of the bins below it. Once I get to this third bin, take its frequency, 1, add up the frequencies below it. So 1 plus 3 plus 5, which is 9. So we could have broke this down, right? here's kind of that first bin, here's the second bin, and now here's the frequency of the bin that we're looking at, right? So that's why when we're in Excel, another way we could have thought about the cumulative frequency is, well, if I take the frequency of the current bin that I'm looking at 1 and add to that every bin below it, well, remember, the cumulative frequency of the bin underneath it actually added up all the bins that were below it, right? So that's why we kind of use that, I guess, different kind of method in Excel when we just copied it down. It makes it a lot easier, right? I think intuitively it makes a lot more sense to think about it as like this plus this plus this plus this, but adding in the previous cumulative frequency kind of gave us that shortcut and saved us a little bit of time, okay? Any questions on that before we keep moving? All right, let's see. Okay. All right, so once we have these, since this way was a little bit more tedious, I'm actually gonna move this title over here and delete that cell. Okay. We can do the exact same thing for cumulative relative frequencies. It's the exact same process, but instead of taking the frequency of the current bin and every frequency of the bins below it, we'll take the relative frequency of the current bin and look at every single bin below it, right? So the shortcut we had was, for the next bin, take its relative frequency, add to that the cumulative relative frequency of the bin before it, so cell 07 there again. And now when I copy this down, oops, I went too far, it'll put in my cumulative relative frequencies. Okay? Now there's another way you could have done this. So just like to go from frequencies to relative frequencies, we divided by what? So how did this 37 become 0.71? We divided 37 by total number of observations, right? That's what we were doing here. Same kind of thing. If we want to go from frequency to relative frequency, we divide by the total number of observations. If I want to go from relative frequency to cumulative, if I want to go from cumulative frequency to cumulative relative frequency, I would also just divide by the total number of observations. So I could have done it this way, or because I had already calculated my cumulative frequencies, I could have just taken those and divided them by my total number of observations, which I had calculated down here. Okay? Now, when I copy this down, I want N7, I want that reference to update, but I don't want the total number of observations cell to update. So I'll freeze that using $signs. We've talked about this quite a bit at this point. Now, when I copy this down, I get the exact same answers, right? Just two different ways of doing the same thing. Okay? Now, this step here, I didn't have to calculate the cumulative frequencies first. I can go right to calculating my cumulative relative frequencies. But if I did have those cumulative frequencies, I can turn them into cumulative relative frequencies by simply dividing by the total number of observations. Right? So notice that cumulative relative frequency, once we get to the last bin, it should always be equal to 1, right? The cumulative relative frequency. Because by the time we get to the last bin, every observation will be counted in at least one of these bins, so we should have counted the proportion of the data that we have counted at that point would be 1, all of it, right? Any questions on any of that? I'm going to see one of these cells again or clarification on anything. Okay with this? All right. Is there anything else I want to say here? Oh. So one thing that I did not mention on Monday, but we calculated histograms here, by getting the frequencies, relative frequencies. We then inserted kind of these histograms or these column charts, and we're calling them histograms, right? So this process gets you used to using Excel to do things like cell references, freeze cell references, that count ifs formula, the min, the max, the sum function. It's going to get you used to using all of those, which we're going to continue to use for other things in this class. Okay? So when you go to that first Excel assignment, which I'll post Friday after class, we should have worked through everything Friday that you would need to kind of start working and get through that assignment. I want you to set things up similar to what we did here when you're creating things like histograms. Okay? You will not get full credit, or likely hardly any credit, because most people that do it this way aren't able to figure out how to do it correctly. But if you Google histograms in Excel, they will tell you to select the variable that you want to create a histogram for. Excuse me. They'll tell you to go to Insert, and there's this statistics chart option, and there's this histogram, right? So it'll give you a histogram. However, notice these numbers it automatically generates. You can go back into some of the settings and like play around with this to try to get this to be exactly the numbers that you want, but it's a lot more difficult to deal with. Right? Notice it doesn't start at 0 here, right? There's some issues with it. So I don't want you to use this kind of built-in histogram tool. When I ask you that in the Excel assignment, I want you to go through the process of setting it up like this. More so you're set up well for future assignments, right? Because we're going to be using this COUNTIFs function again. We're going to be using cell references in the way that we did here. We have to freeze some cells again. So I want you to use this process. The other thing, this process, it's a lot easier to kind of get the exact values you want for your bins. It's also good in practice if things ever change, like you want to change your bin length. It's good because it automatically updates everything, whereas the other one doesn't. You have to go back in and play with the options again. It's not near as easy. Whereas here we change the bin length in one cell and it updates everything for us, okay? Didn't make a lot of sense because I put in a weird number there if it changed, but I just wanted to show you that it will update everything, okay? Any questions on that before we keep moving? Okay. All right, so, you know, we could graph those cumulative frequencies. I didn't show you that, but it's pretty easy, right? I just select my labels, hold Control or hold Command on a Mac. I'll select my cumulative relative frequencies. Usually when we graph cumulative frequencies, we'll use a line chart. And now here's my cumulative frequency graph, or I think the book calls it cumulative frequency polygon, right? Same kind of thing, okay? So that's pretty easy, not a whole lot new there. So up to this point, we've really focused on one variable, right? But we might want to know, well, what's the relationship between two different variables, right? I don't just want to know the distribution of a variable. I might want to know, well, I have this variable X and this variable Y. How are they correlated, right? How are they both, you know, when one increases, does the other increase? When one increases, does the other decrease? So an example data set we would have for this is I have two variables here, a bunch of different countries, but I've got health expenditures per capita and life expectancy, right? So I might think that as, you know, countries spend more per capita on health, maybe that they tend to have longer lives, right? So I'm going to use this health expenditure as my X variable, life expectancy as my Y variable, okay? So I'm going to copy and paste these. I already have this. You don't have to copy and paste them, but I already, before I posted this file, copy and pasted them into our Excel file, right? So I'm going to delete this. How can I create a scatter plot? So what a scatter plot does is basically takes these two variables. The first variable, or the variable on the left, it treats as the X variable. The variable that you select that's on the right, it'll treat as your Y variable. So if you highlight this data to input a scatter plot, it's going to take every observation and plot that point. Use that X and Y coordinate to plot a point on the graph, okay? So I'm going to highlight this, go to Insert. I'm going to choose this option down here where it's got a bunch of dots, scatter plot, and it puts every single observation is plotted here. And this kind of can give me an idea. If I try to think about a line of best fit through this data, you know, maybe it's slightly increasing. The data is a little bit varied here, so maybe it's pretty flat, but it might slightly be increasing. So maybe that it looks like there is somewhat of a relationship as more money is spent on health, life expectancy might go up a little bit, but also, you know, here they're all spending a bunch of different values and their life expectancy is all about the same. So maybe there isn't a real relationship between these two variables. It's kind of hard to tell from this data set. But some data sets are very obvious, right? Once you get that scatter plot, it looks like almost like a block of the observations. So you can see a really nice upward sloping line or downward sloping, right? It gives you an idea about what the relationship is between these two variables pretty quickly. it also gives you a nice visual where you can identify like what is going on here, right? Like this country, you know, what country is that? I might be interested because they're spending a lot of money on health and they have the second lowest life expectancy of these kind of OECD countries, right? Well, sure enough, if I investigate, that's the United States, right? So it's kind of an interesting, I might want to dive in and see, well, why is that the case, right? But it allows me to really easily see that with a nice visual pretty quickly from a scatter plot, okay? And here we have some other countries. The next one we're going to go through, we talked about this type of data, but this type of data allows us to make a really nice visual that will be useful in like if you're giving presentations on something. So here I've got one subject, the United States, at several points in time, right? And I've got the unemployment rate for each one of these years. Okay? In the, whoops, I want to exit out of this so I can Excel, there we go. I have a US unemployment worksheet here in the data file. I'm going to get rid of this real quick. So I've got, I think the ones in the slides was truncated, so I actually have from 2005 to 2020, and I've got every single unemployment rate for each of those years. Okay? What I can do is if I highlight this data, all right, and I go to insert, and I want to put a line graph, I might think, okay, well, yeah, it'll use, you know, the x-axis will have my years, and then the y-axis will just have plotted the unemployment rate and a line that connects them all, so it'll kind of tell me, like, has the unemployment rate been going up and down in certain years, right? So I go ahead and I try to do that, but what ends up happening is it treats both of these as y-axis values and essentially plots two variables for you. That's not what we wanted, right? This variable of year, this was just identifying what the year was, right? And we were hoping that was going to be what was on the x-axis. So to create a time series graph, what we have to do is highlight the variable you want to put on the graph. So we'll go insert our line graph. Perfect. You guys see unemployment's going down, then up, then down, then up. But I don't know what years these are. This could be the 1970s for all I know, right? So the way that I can get those years on my x-axis here is I left click on these numbers. It puts this little box around them. I then right click in that space and it gives me the option to select data. I hit select data. I've got these horizontal axis labels. I'll hit edit. And instead of just being 1 through 16, I want them to be these years. So I highlight the years and now it automatically puts them on there on my x-axis. Okay, so we hit the OKs to get back. I'm gonna make the chart a little bigger. Okay. So all I had to do there was left click on the numbers, right click, select data, edit the axis labels, and highlight the years that were in my data set, and then click OK. All right? I think we did that last class for, oh, what did I show you? The bin labels. I think I showed you, even if you forgot to select them, you can put them in after the fact using kind of the same process. Okay? But the reason why this is really nice is because it very quickly allows me to tell a story, right? Mid-2000s, unemployment kind of hovered right around 5%, increased in the late 2000s, peaking at 2010, and then kind of slowly declined up until 2019, and then we saw a pretty big spike in 2020 for obvious reasons, right? So it allows me to tell a real quick story through time about this one variable just from this visual depiction, okay? I want to make up a bunch of numbers real quick so I can show you something. So it won't make a whole lot of sense, but all right. Oops. So let's say here I have Canada. Let's say this was Canada's unemployment rate, right? What I can actually do is highlight both of these variables. It'll plot both of them. So I'll have a time series graph of Canada and a time series graph of the United States unemployment rate over this time period. So I select the data, go to insert, line graph. Notice now I've got my United States time series graph for unemployment and my Canadian unemployment, right? So I can, and then same thing there, to change the years, you know, I go to select data, edit my axes labels, hit OK, hit OK. Okay? Any questions on any of that? probably ask you to kind of make one of these time series graphs and then kind of decipher it or tell me a story, just kind of like I did with the unemployment rate. That'll be one of the things in that Excel assignment, okay? All right, so that should be good. So we got our time series graphs out of the way. What is that? I don't know, that's weird. We're going to talk about a couple different types of distributions, and then we're going to go into talking about things like the mean. Hopefully I can tie these together. We ran out of time for me to completely tie these two subjects together in my last section, so we might kind of miss out on time together, but hopefully we'll get close. So, you know, we've seen how we can take data now and get a frequency distribution for a data set, right? And that frequency distribution really tells us, you know, if we go back here, maybe, there we go, where like the majority of the responses are, right? Here we can see that the majority of responses are right here. But if we had even more bins, we might get something that looks like this, right? So we created a lot more bins here and then counted the number, and this was that SAT score. So this is like the average SAT for high schools. We can see that there was very few high schools that kind of had averages in these lower ranges. A lot had kind of average scores right around 500 because that had the highest kind of frequencies. So this, you know, if we were to take one of these frequency distributions once we graph it, a lot of the times we'll see certain shapes. So with this one, if I was to draw a line that went through the top of every single one of these bars, roughly it would look like kind of this symmetric hill or like this bell-shaped curve. Now, we have something a little weird going on right here, but for the most part, it kind of looks like it would follow that line, right? Anytime we still see this bell curve, we call this a normal distribution, right? So, you know, we see this pop up a lot. We'll start talking a lot more about this probably in a month or so about the normal distribution, and we'll focus on it for the large majority of this class. But it allows us to do some really cool things, okay? It also just is bizarre and pops up all the time. So like I always give examples, you know, human height, human weight. If you look at like athletic performance, not of athletes, but just like general kind of people, a lot of it follows a normal distribution, right? So it's very interesting. It pops up all over the place. And we'll see it a lot. What if I had like a example I used a lot last class was this income idea, right? So let's say I've got how many people make between 0 and 5,000, 5 and 10, 10 and 15. Looks like their bin lengths are about 5,000 up until they get to kind of these higher ranges. And then they say, okay, how many people make between 200 and 250,000 and more than 250,000, right? So they kind of create these catch-all categories at the end. But you can imagine I could actually continue to do these in $5,000 bin lengths and it would just extend very, very, very far, right? Well, if I try to trace a line that goes to the top of each of these bars, you get something that looks kind of like a hill, but it's just got this really long right side and a really, really short left side, right? So this long right tail, we'll call this a right skewed distribution, okay? We can't see negative income amounts, but we can see amounts that are really, really high. So that's how we end up with this really long right tail, but like a really short kind of left tail here, okay? If we had like length of a pregnancy, so gestation weeks of a pregnancy, and we were to plot that, you know, most children are kind of born right around what, 38 to 40 weeks, right around 9 months, but we do have some premature births as well, right? Now, on the other side, you know, we can see children born at, 6 months, right? We don't often see, so that's 3 months early. We don't often see a children born after 12 months, right? So there really isn't a right tail on this variable, but we have kind of this longer left tail, right? So we would call that a left skewed distribution for that variable, okay? And then kind of the last one, if I was trying to draw a line through this, it would almost look like I have almost like two normal distributions, right? Just kind of next to each other. So this is body mass, right? And we call this a bimodal distribution. Excuse me. So why do you think if I was to just take a data set with a bunch of different individuals and their weight, why might it end up looking like a distribution like this? So if I have a data set of people, like let's say I just start asking people walking around campus what their weight are. It's probably not going to go too well. But what is one characteristic that might cause there to be one group with a much lower body mass than the other? Weight, if weight doesn't quite convince you, think about height too. Well, age, but even if I had the same age individuals, if we look at males versus females, kind of the average height and weight is just higher for males. And so when you look at weight and height, they follow normal distributions within each gender. So like male height and male weight looks pretty close to a normal distribution. Female height and female weight looks pretty close to a normal distribution. But kind of female height and weight on the average is a little bit lower, right? So you can kind of think about here is likely my females, and then here would be kind of the weight for my male distribution, right? So anytime we have a characteristic that might cause a difference in like the average of two different groups, we might end up seeing a bimodal distribution, right? And that's kind of what this signifies, okay? So how can we get measures of, if we think about now, well, geez, I got this bimodal distribution. I'm thinking about the differences in averages of groups. We haven't even talked about averages yet, right? So a lot of times when we see these frequency distributions, we can get a pretty good idea about where the middle of the data might lie. But we might want to just come up with actual statistics that tell us the values for what that middle part of the data is. When I say that middle part of the data, this is the idea of like central tendency. Where was the majority of the data lie, right? Or where, if I'm trying to use one number to capture kind of every observation, where's kind of the middle of this data set? Okay. So a lot of the times you probably think about this as the average, right? I think we all do in our everyday lives and kind of a non-statistical kind of mindset. But we actually have 3 different measures for where the middle or the central tendency of a variable is. Okay. So the first one is kind of probably the one that we've seen in other classes is the mean, right? So we'll notate kind of using this Greek letter mu, right, the population mean. Now, if we have a sample data set, we can still calculate the mean. It's going to be the exact same process, which we'll go over here in a second, but we're going to notate that with X bar. So anytime we're looking at sample statistics, it's usually written in kind of our normal kind of English alphabet. And then the population, if it's from a population data set, we notate that statistic with a Greek letter. Okay? So here's the letters we use, or the symbols we use for the mean. Median and the mode, a lot of times we don't notate the difference between a sample or a population median and mode. If you wanted to, probably what would be appropriate here, here's our population median mode. Use a lowercase m for the sample, but I'm never going to kind of throw a question at you that tries to kind of trick you with that. We really treat samples and population the same with the median mode, so we usually just use the same notation. Okay? So M subscript D is the median, M subscript O is the mode. We won't talk about these today, but maybe a little bit on Friday and definitely next Monday we'll have a lot of discussion on this, or measures of variation in the data. So there we'll use kind of sigma squared, right, this Greek letter. This will be our population variance. S squared will be our sample variance. And then same kind of convention, this other measure of variation we have is the standard deviation. We'll use sigma to represent the standard deviation and lowercase s to represent the sample standard deviation. And you kind of notice we're really just scaling the variance, right? Taking the square root of the variance to get the standard deviation. But this is the notation that we'll be using. Right? And we'll see this again for the measures of variation. But today we're going to kind of focus on this central tendency. Where are we at in time? Okay. So we've got the population and the sample mean, right? Really, this is usually what we think about as like the average. So if I had 5 numbers, how would I find the average or the mean? I know some of you have had to have been able to find an average for a class at some point. Add the numbers up and divide by how many numbers you have. That's the easiest way to say it, right? If I was explaining this to like a really, really little kid, that's how I would do it. Add the numbers up, divide by the number of numbers you have, right? If we want to be a little bit more technically correct with some of the things that we're going to do moving forward, this population mean we can think about as, if I had a data set, I'm taking the first observation's value for that variable x, adding that to the next observation's value for that variable I'm looking at, x, add in the third, all the way to the very last observation, right? I'm just adding up all the numbers for that variable. Okay? So capital N here represents the total number of observations in my population data set, right? So that's why I go from the first to the very last observation, add up all those values, and then divide by the number of values that you had, the total number of observations. Now we can write that a little bit differently up here, which is using this summation sign. So this Greek letter, capital sigma, is our summation sign. All this says is start at the first observation, use the value for whatever variable x you're interested in from that first observation, and then add up all the values for that variable from the first to the very last observation, right? So take this variable x, for each observation, just add up all the values, which is really what we'd have kind of written here as well. It's just another way of writing it out. And then divide by the total number of observations that you had, okay? I don't think that should be too bad. The sample mean is the exact same thing, but instead of the number of observations in our population data set, we're going from the first to the last number in our sample data set. So lowercase n represents the number of observations in our sample data set, okay? But practically, there's no real difference, right? Whether I had a population or a sample data set, let's say I want to find the mean birth weight in the US, I would take every single birth I had in my data set, add up the weight of every single child born, then divide by the total number of children that were born, and I have my answer, right? So like I said, I'm sure a lot of you have done this before. I'm kind of, probably a little bit rudimentary here, but we're just kind of reevaluating and thinking about the exact formulas, right? So when it comes to like the exam or something, I'll give you like a formula sheet that you can use, so you don't have to have these memorized. But really, I want you to be able to think about how this is written mathematically, what that really means, and how we can translate that into a process that maybe we can remember a little bit easier. And here, it's just add up all the values and divide by the total number of values you had, okay? So if I had an example where I've got some game and a bunch of different points scored, so this could be basketball, it could be boggle, I don't care what game it is, how would we find the mean here? Well, we just mean points scored, sorry. Well, we add up all these points scored, right, from the first to the very last observation in our data set, divide by the number of observations we have, which here we have 7 games. So just add up all those values, divide by 7. I don't think this should be wildly anything too crazy yet. So we'll deal with a different data set. It's the exact same process. But here, let's say I give you these answers, right? So I've got all these employees, 7 employees, and their commute times to work. And here's the possible, I asked you for the mean. Well, without even breaking out your calculator and just looking at this data set, right away you can rule out a couple of these answers. So which ones can you rule out and why? Yeah. Yeah, why? Yeah, my lowest observation is 20. Remember, don't get like lost in the formula. If I had like started adding these numbers up in my calculator and then I was going to divide by 7, but like I somehow missed with my finger because I was going quick and hit 3 or something, and I end up with some crazy answer. Well, don't get like married to the formula, because like you can make mistakes in the calculator. But let's say you made a mistake and you saw 15 on your calculator. Well, right away you look at this data and you're like, this is lower than the lowest observation. I'm calculating a mean, which is supposed to be what's the middle point of this data set. Well, my lowest value is 20, my highest value is 90, so my mean has to be somewhere in between those two values, right? So right away, 15 doesn't make sense because it's outside the range of even the values that I see in the data set. Same kind of thing for 95. 95 is greater than the highest value of my data set. I'm looking for the middle point. How can the middle point be outside the range of values I see in the data, right? It doesn't even make sense, right? So we could rule out A and C, and from there, it's just a matter of to pinpoint it down between B and D. Probably just going to have to calculate this, right? But remembering these things, remembering what the statistic you're computing actually tells you, prevents you from making some of these common mistakes or these like stupid mistakes, like hitting the wrong button on a calculator, okay? So we go ahead, we add up all these commute times, divide by the total number of observations we have, which is a 7 again, and we get a mean of 45. Okay. So, is everybody okay with that? Before we kind of move on, we'll talk about the mode a little bit here. Good with that? Okay. So the mode is just going to be the number that occurs most often in a data set, right? So basically, if I had a variable, for example, that was like the number of children in a household, and I count the number of responses I see for 0, the number of responses I see for 1, whichever one of those values had the highest frequency, that's my mode. It's the number that occurs the most often, okay? So if I go back to this example, and I think I have a slide for it in a second, but I want to go back. You know, what would the mode be here? This one's actually, I start to count like, yeah, the only number that happens more than once is 35, so it has to be the mode. You know, with a small data set, the mode isn't necessarily as informative about what the data looks like because, you know, I could have 7 different numbers here and then I don't have a mode, right? They all happen once, there's no mode. But with larger data sets, you can imagine, like let's say I've got a huge company and I've got thousands of employees, I could find a mode commute time, right? There's gonna be one commute time that happens the most often because of, you know, whatever the housing availability is in the area or, you know, so with a small data set, sometimes finding the mode, you know, in that one, we only had one number that happened more than once, so it's a little bit goofy, right? The median is going to be, you know, it's the middle value of the data set. So a lot of times if you heard that, you'd think, oh, it's the mean, right? It's the same thing. Well, no, the mean is accounting for what the actual values are, right? We're adding up all the values and dividing by the total number. The median just says what number is in like the middle place of the data set. So essentially what you would do is you would arrange the data from smallest to largest, right? So let's say I had 101 observations. I cross off the very first or the lowest observation, cross off the 101st or the highest observation. Then I go to the value that would be in the second and 100th spot, cross those out. And I keep doing that until I'm left with that 51st position. Whatever value is in that 51st position, that would be my median. Because I would know there's 50 observations below it, and there's 50 observations above it. It's exactly in the middle of my data set, okay? And that would be the value that's my median. So that works out really nicely if I have an odd number data set. But let's say I have an even number data set. I'll make it an easy one. Let's say that I have 4 observations. So I cross off my highest, cross off my lowest, cross off my next highest, cross off my next lowest. I don't have any values left. So what I do is I cross off the highest, cross off the lowest. I'd be left with those 2 values in the middle. To find the median for an even number data set like that, once I have those last 2 numbers in the middle, I'll just take the mean of them or the average of them, right? So we'll go through an example here in a second where I'll do an even number data set, but it doesn't really make it that much harder, but one more step there if we really want to get at it, okay? So we'll walk through, 7 minutes, so. What would the mode, we already talked about this, 35. What would the median be? Well, I didn't arrange these from smallest to largest, but we can kind of, with a small data set, probably do this just by eyeballing it pretty easy. So highest value is 35, lowest value is 15, so I'll cross those off. Next lowest is 16, next highest is 35, I'll cross those off. Next lowest is 18, next highest is 28, and I'm left with that value of 20 right in the middle, such that there are, you know, if this is my median, 1, 2, 3 values below it, 1, 2, 3 values above it, right? It exactly splits the data in half, okay? Is that process clear? Anyone need clarification on that? Like I said, with a small data set, you don't have to reorder it, especially with larger data sets and things. It's really easy to just rearrange them or sort them from highest to lowest or lowest to highest, okay? I think I'll skip this example just because we'll go through something else, but you know, you could rewrite them, arrange them in order, cross off the lowest 3, cross off the highest 3 with a different data set. You know, this is just really another question if you're going back and kind of reviewing things. Here's just another example, okay? So what I wanted to go through though is kind of highlighting some differences about these 2 things, okay? So I'll give you a small data set example, and then I'll probably go back to the formula and point out why this happens. But let's say I've got a small data set. It's 4 numbers, right? 1, 2, 3, and 4. What would be the median of this data set? Well, cross off my highest, cross off my lowest, left with two values in between. So I'll take the average of those. So 2.5, right? What if I wanted to find the mean of this data set? So if I wanted to find the mean, I'd add these numbers up and divide by, I've got four numbers, so divide by 4. So 1 plus 2 plus 3 plus 4 is 10, divided by the number of numbers I have, which is 4. I actually end up getting a mean that's exactly equal to the median, right? And if you know, kind of alluding to some things we'll talk about in the future, but the reason why that happens is if we have a symmetric data set. Okay? Let's say instead I have an outlier down here, or a really extreme value of 100. The data set hasn't changed much, but if I'm using these statistics to describe where the center of the data is, now, kind of call this after the second data set, right? Actually, it might be easier to do that. No, because that looks like squared. All right, we'll just use a little tick then. So what's my new median? What would I do? How do I find the median? It's 2.5. Why? Cross off my lowest, cross off my highest. I'm left with these values. Take the average. Right? What's the mean here? So it's 2.5. What's the new mean? I add these numbers up. So I get what? 106 divided by the number of numbers I have, which is 4. So 26.5, right? So when we have these extreme outliers, especially in small data sets, notice they greatly influence the mean, but they don't influence that median at all, right? So especially with small data sets, the median really gives you a better idea about like where that middle point of the data is, because these outliers have a lot more influence on the mean. You know, with the median, we're crossing them off. But with the mean, if we go back, they get added into that numerator. So if we have one really, like, let's say we're doing income, and I got someone in there who's making $3 million a year, that's going to greatly influence my mean because it gets added into that numerator, okay? With a median, that number just gets crossed off, right? That's the highest number, it just gets dropped off, right? So a lot of times with smaller data sets, we want to look a little bit more at the median than we would the mean. Now, as we get a higher number of observations, one really extreme value doesn't carry as much weight, right? We'll talk a little bit more about this idea of weighting once we kind of move to some topics here in the next couple classes. But with small data sets especially, a lot of times that mean can be greatly influenced by one extreme value, but our median isn't. And so that makes it sometimes a little bit more reliable, okay? Any questions on that? All right, so we work through this. How far do we get? So we got to here. So I think maybe we'll leave this on a cliffhanger, I guess, today. So we'll kind of revisit this idea of medians or means and medians next class. And I'll relate this to what we were talking about with those different distributional shapes. Okay, so we'll pick up on here next class. We'll then start going into measures of dispersion. Get that online quiz done today. I'll post it as soon as I get back to my office. It should be pretty easy. Get that chapter 3 Learn Smart done. We'll really start diving into some more of the complicated stuff from that chapter on Monday, okay? All right, we'll see some of you guys on Friday if you're on Zoom, and those of you who are here, I'll see you guys on Monday, right? Because that would be your next class, okay?